Our next speaker is Jeff Boudier, who leads product and growth at Hugging Face, which is one of the creators of Transformers, the famous Transformer libraries, with the aim of democratizing the state-of-the-art in machine learning and NLP. Previously, he held leadership positions at business development at GoPro through the acquisition of Stupeflix, which he was a co-founder of. Jeff, welcome.
Hi, thank you very much for having me. Can you hear me okay?
Yeah, we can hear you.
Excellent. Can you see me okay?
We can see you. When you start presenting, I'll let you know when we see the screen.
Beautiful. And can you see my screen?
Yeah, we see it now.
Awesome. Well, thank you very much. Super happy to be here. Thank you, Kushal, and the organizing committee for inviting me. Machine learning efficiency is super important for us, a central theme to what we do. So I'm super happy to tell you how we go about industrializing state-of-the-art, by state-of-the-art machine learning, I mean transformers, how we accelerate them so that as many people as possible can benefit from them. So yes, to a 100x speed up and beyond. Just a bit of a housekeeping. If I'm not able to take your questions live, or if you have any about anything that I'm about to say, please reach out to me directly. My email is jeff@huggingface.co. Jeff Boudier, happy to answer any of your questions. So in this talk, I will have some research results to share with you. But to be honest, the talk is not really so much about science as it is about engineering, as it is about how do we take this latest science and enable developers, then companies, and eventually people to use and benefit from these state-of-the-art models. And that's sort of the hard work that I want to walk you through, how we're able to accelerate those models to have fast inference, which we do through our machine learning platform and hosted services, but also through our work with our partners like Intel, which I will talk about a little bit later. And no, we didn't synchronize this with Gadi. This is a coincidence, but I'm excited to share with you how we work with Intel to industrialize transformer models. So before I get into the meat of it, I thought to start with a little guessing game, which is probably very obvious for all of you. But the question here is, what is the common link between the Tesla Autopilot, Gmail autocomplete, Facebook translation feature, and search results in Bing? And I think to all of you, the answer is quite obvious. The common link is the transformer model. It's through a transformer model that your Tesla, if you're lucky to have one, can make sense of what the camera sees into the vector space. It's through transformer that Gmail is able to predict how you are likely to finish your sentence mid-sentence. It's through transformer that Facebook is able to automatically translate posts to over 150 languages. And it's through transformer that when you ask Bing a question in natural language, it's able to actually understand and retrieve the information that's relevant to your question. The other piece that's maybe less obvious here is that the common point between these four use cases of transformers is that each of those requires billions of predictions a day. And that's why for us, industrializing transformers is important, because what is Hugging Face if it isn't Transformers for the rest of us? Today, there's if you're not Google, Facebook, Microsoft, Tesla, there are rare cases where companies are able to deploy transformer models at a scale that enable real-time inference for all of the company users or customers. And so through Hugging Face, we make this latest science available, accessible to as many people, companies, languages as possible, but we also want to make it as efficient as possible so that these models can benefit people without connectivity using their phone, for researchers who don't have access to A100, etc. So to tell you a little bit about the history of Hugging Face, I need to tell you a little bit about the history of transformers. And we talked about the seminal paper from Vaswani, attention is all you need. The central theme, the central idea for us is transfer learning. That is the ability to efficiently create a state-of-the-art that will produce great predictions to your task, to your business data in a very efficient way, using less data, using less compute resources through transfer learning. And that is one of the main benefits of transformers, is that you can leverage the immense data corpora, the immense computing resources that have been leveraged to produce those pre-trained models, to then very efficiently create specific versions that work for in specific context downstream. So that in itself is a huge efficiency boost that is inherent to using transformers. So the pace of innovation since the introduction of BERT has been breathtaking. I won't go too much into this. You guys are familiar. I think one striking fact is that it only took 6 months for Squad 1.1 to be overcome in terms of computers surpassing humans. And so it only took 6 months for Stanford having to release Squad 2.0, which then again within months was surpassed related to human performance. And so in this world where the progress of the field is accelerated, our mission at Hugging Face is to democratize NLP, or was to democratize NLP. Because today I say democratizing machine learning, making the latest state-of-the-art science, machine learning science, available to as many people as possible. Because transformers, in a way, are eating the world of machine learning. We introduced various architectures for speech, transformer-based speech tasks within the Transformer open source library. The traction for these models and tasks is really amazing, with hundreds of thousands of downloads of models every month. So where Transformers has sort of conquered NLP, and that has been done for a while, like this is quickly expanding to other modalities, and vision as well, with a very active community building upon vision transformers, DALI, CLIP, and other computer vision and multimodal architectures to further the scope, the transformative scope of transformers, providing amazing accuracy with efficient training mechanisms. All right, so I'm used to showing this graph, and by now you're probably familiar with it. I'm only the 4th person today to show you this. It's also sort of old news because I stopped before GPT-3 was even introduced. The trend was already clear. Charting here the introduction of new model architectures by their number of parameters. The exponential curve was already there 2 years after the introduction of BERT. And so one thing that's, well, two things that are important to us at Hugging Face, and I think to us all at this workshop, is that this exponential curve creates these challenges for machine learning engineers all over the world to take advantage of those models that require specific hardware, amounts of memory that make them unwieldy to deploy within existing infrastructure productions, within customers' compute environment. But the less obvious trend on this chart is as the size and compute requirements to introduce these new model architectures increases exponentially, the relative contribution of public research labs and universities starts to ebb away. And that's also a concern for us as an independent, open, and community-driven company that wants to democratize machine learning because we need a world in which the scientific community can continue to build upon each other's work. And so it's very important that the ability to push the state of the art be not limited to the biggest tech companies in the world. All right, so going back to our mission to democratize machine learning, how do we do this? We do this through two pillars. I just talked a bit about community, but the other is efficiency. So what do I mean by community? Well, while Hugging Face is a company of 70, my accent goes in the way of getting the number across. But while we are a team of 70 people, we really represent the work of over 1,000 open source contributors and many more model and dataset contributors to our community and to our open source and platform. Today, we host over 10,000 state-of-the-art community models across NLP, speech, and vision tasks. So whatever task, dataset, model library you're looking to leverage in your work, there is a model for that within Hugging Face. We are, in essence, the delivery vehicle for the latest science to make it into the hands of practitioners, of developers, of scientists. And of course, languages, which is a very important component of our mission. To democratize machine learning truly, we need to make sure that everybody across the world benefits from it. And that means whatever language you speak natively, these models exist, are pre-trained, are fine-tuned to you, whether it's a language model or a speech model. So yeah, we are lucky to have a very active community to support us in making sure that all the latest model architectures have checkpoints available in all different languages of the world. This approach to building technology in the open and do it in a community-driven way has really propelled the growth of adoption and usage of our open source library. What I'm charting here is the GitHub stars over time in red for our main open source library, Hugging Face Transformers, along with other awesome open source projects. The main idea is that the growth of adoption of transformers is really unprecedented, definitely for machine learning, but perhaps for open source as well. Today, the library is downloaded over 2 million times a month. So it is the reference toolkit through which people, practitioners, researchers are able to access those models. I talked about community. The other pillar is efficiency. And so efficiency has been, since the beginnings of the Transformers library, a main area of focus. This is how we're enabling independent researchers to do state-of-the-art work. It's how we're enabling models to consume less energy on aggregate. And to run in as many diverse computing environment and platforms as possible. Some of the latest methods which we've pioneered over the last 2-3 years, of course, distillation, introduced by Victor, Hugging Face researcher Victor Sahn, obtaining through knowledge distillation a version of BERT, distil BERT, that keeps 98% of its performance on glue while producing a model that is 40% smaller and critically 60% faster. Movement pruning or soft movement pruning, new method of unstructured pruning introduced also by Victor and also Thomas Wolfe, our Chief Science Officer, and Dr. Rush. A method through which we're able to drastically reduce the memory requirements of models, to radically reduce the density of models. And a latest technique, block sparsity, to introduce structure pruning around block sparsity to make sparsity compatible with hardware kernels. And I'll go into a little bit more detail to share our latest results on this theme a bit later on. But before I do, I want to go back to the engineering and walk you through our approach on accelerating models for our customers. And what I mean by our customers, so how do people use transformers today? I'm putting here some classical sort of NLP use cases. So I talked about Bing using question answering to be able to retrieve information, answering questions asked in natural language by users. Information extraction also used, for instance, by Chegg to be able to associate data based on named entity recognition. This is how many large companies, including Monzo, are today accelerating and automating their customer support by understanding from the customer ticket where they should route, what is the priority of the support request. And of course, to also create new information like summarization, which is heavily used in the financial services industry, to make sense, to expand or contract the information contained in text. And by many AI companies and companies to power conversational experiences so that customers can have faster, better responses when interacting with them. So these are the use cases, but then how do you bring that to companies and practitioners? So we're building the machine learning platform to accelerate transformers adoption from training to production. It's a complete tool set for AI teams to be able to manage their assets, models, and data sets, to experiment and build apps and demo them with their colleagues, to train new models easily, leveraging fine-tuning in a very easy way. And critically, that's the piece that I want to talk to you about today, to make use of those models, to serve them to their customers within their apps in a much accelerated way. In particular, for some architectures, we're able to speed up by 100x the inference of these transformer models. How do we go about that? So yeah, I want to talk about the Accelerated Inference API service, in particular, how we're able to speed it up so that it can be integrated in experiences which require real-time interaction with the customer. And remember, we host over 10,000 different transformer models on the hub. We need to be able to serve and accelerate all of them. If you boil it down, it's really 60 to 65 different architectures that have been implemented within the transformers library. So it's a very sort of wide problem space. But to get to these 100x acceleration, the first 10x are all about optimizing that open source implementation. And the example that's represented here is one which represents the GPT-2 encoder-decoder sort of architecture when generating one more token. And you can read more about this in our blog at hf.co/blog. There is a whole write-up about this. The main idea here is that in the sort of a naive implementation of the GPT-2 model, you would, for every new token, so here I love puppies, 4 tokens represented there. For every new token, you would have to recompute all of the attention embeddings, matrix multiplication based on the new token. And in the fast implementation, which we're able to leverage, we use all of the already multiplied matrices from the n-1 sort of tokens when computing the new token, which is producing an order of magnitude efficiency in the computational cost. An efficiency that obviously grows in a compounded fashion the more the longer the sequence you're generating is. So that's an example of how we are able to accelerate like one specific model architecture. Another way, which is transversal to all of the NLP architectures, is the tokenization process. So tokenization happens to be typically one of the bottlenecks in inference latency when deploying models. And we've recognized that and re-implemented tokenizers for the architectures that are implemented in the Transformers open source library in Rust. Which yielded tremendous acceleration, tremendous speed up for tokenization, of course, but the end-to-end inference as a result. So we called this feature fast tokenizers, was shipped in the 4.2 version of Transformers. Today is the default way of tokenizing when you're calling the pipelines within Transformers. So open source optimization is how we're able to create up to 10x optimization in the inference pipelines, and we're able to make that available, accessible to the whole community. And then to get to the next 10x is when it gets a little more complicated. The next 10x, you have to look in detail at the model architecture that you're considering, and every different model architecture will require different optimization. And you have to look at things specifically, looking at which hardware accelerating libraries are available, data types and kernels are available on that platform to be able to get the best results. So that's, again, very much engineering and not science. It's not one where you can graph results, which customers will be expected to reproduce sort of verbatim. This is an area where to get the best result, you have to look at your model architecture, look at the graph, optimize the graph in the tools available in your library, export it and compile it, but export it and compile it not necessarily in the default way that, for instance, Onyx Runtime or Triton Inference Server will produce. You have to export them in a way that will be optimally compatible with the hardware that you will use to do the actual compilation. And that's why you need to leverage the latest features of the accelerators. For instance, TensorRT8 introduced integer 8 quantization for BERT models. OpenVINO offers acceleration specific to Intel CPUs. You have to put it all together specifically for your use case. That's how you're able to get to the best result. So that's how we're able to accelerate models, transformer models for customers of our machine learning platform. But next, I want to tell you, and I'm going back into the world of science, I want to tell you about how we can go beyond this 100x, how we can accelerate models further. So back to science and back to looking at the model before we look at hardware. So the model, the method I want to talk to you about is called block movement pruning. It's a method that has been introduced by our researcher, François Lagunas. You can find the code today on our GitHub with the NN_pruning library. This method yields 2 to 3.5 speed up results on models on Squad and other benchmarks, while pruning up to 90% of the model weights. So it's reducing the memory requirements drastically and speeding up the models. It's doing these two things at the same time, which is the critical benefit of this new method. And it's doing this, of course, while maintaining accuracy, maintaining up to 99% of the accuracy of models, which makes them still practical for downstream industrial or business applications. So I invite you to check out the resulting models from this work. I talked about the open source library and N_pruning. You can also directly test models on François' Hugging Face page at hf.co/madlag, where many models have been exported through the method, so you can test the inference and download them directly. Here I'm going to be walking you very quickly through some of the methods which are explained in this new paper by François, along with Hugging Face researchers Elle, Charlaix, Victor Sahn, and Dr. Rush. A new paper called Block Pruning for Faster Transformers, which will be presented at EMNLP. So I invite you to attend that session if you want to learn more. So in this paper, we summarize all the experiments and work that has been done on the topic. In particular, we revisit all the different distillation methods that have been explored, all the different pruning methods that have been explored, and describe what has been the winning combination for us in producing a model that has both the least amount of memory required, so the most sparse model, but also the model that produces the highest speed up. And in the journey to that optimal method, so there are three main steps. The first one at the top, which we're representing by having on the square at the left sort of the attention head matrices, and on the rectangle to the right, we see represented the feed-forward layers. The block pruning method, which I mentioned earlier, is basically a movement pruning method where we split up the layers into blocks of, for instance, 32 by 32 or 16 by 16. Multiple combinations have been explored, and go through the distillation process. Then we turn our attention to the hybrid method, where we will continue to use this block pruning method on the attention heads, but we will use soft movement pruning on the feed-forward layers to fully prune some of the layers. So, and I didn't, explain the color coding. Blue is what remains. Pink is what has been zeroed out, is what is sparse. And the last method at the bottom, hybrid filled, where we take the result model from the hybrid method. And then for those attention heads which have been partially sort of zeroed out, the blue lines in the middle that have some pink squares representing blocks of zeros, we then further fine-tune the model to fill those in, and eventually further accelerate the model without losing accuracy. So the main results here, and let me walk you through what I'm showing you. So on the left-hand side, you see experiments as in colored lines, and existing models as in dots, represented by their accuracy on the y-axis, and the speed up throughout the experiment on the x-axis. On the right-hand side, you see the same experiments with the colored lines, and the same existing models as dots. But here we're plotting the density, so the inverse of the sparsity, the fill rate, across the same F1 accuracy metric. So let's start with the blue line. The blue line is the movement pruning, which is the paper that I had shown a few slides ago, introduced by Victor, Sahn, Dr. Rush, which has historically been the method through the most efficient method to reduce the computational complexity, to reduce the fill rate of models, but has limitations in terms of speed up, both because it is unstructured pruning, and also because only few hardware platforms have sparse kernels that translate these unstructured sparsity into efficiency gains. So the blue method, the blue line method, as you go through the experiment, on the left-hand side, you're going from the top right to the top left to the bottom right. You're going to speed up the model while sacrificing some accuracy. On the right-hand side, as you go through the experiments, you're going from the top right to the bottom left. That is, you're sparsifying the model while sacrificing accuracy. You're decreasing the memory requirement of the model while sacrificing accuracy. So the block pruning method, the structured pruning method, is the orange line. And you can see that starting from the 88.5 F1 accuracy of BERT, going through the block pruning, fine tuning, we're able to get a much more significant speed up here, up to 2.3 speed up of the model, while losing accuracy in a much slower way. And when you combine block pruning with movement pruning, and that's what you start seeing with the green line, you can get both the speed up and the sparsity benefits. So that's the real, I think, benefit of the method, which is then further improved through the hybrid field method, the red line, which is then further improved through the hybrid field large teacher method, which use the same distillation method, but using a larger teacher, BERT large here, as the teacher through the distillation experiment. We're able to get both the speed up and the memory benefits. So we're hoping that this method, which we've verified on various NLP benchmarks, including encoder-decoder models, and which is also robust when using in combination with quantization, will help reduce the overall energy consumption of transformers models. And we hope that will also enable more privacy in the world, as these models are able to run directly embedded into people's hands. We're working with our partner Qualcomm on enabling more and more models in an embedded way. All right, so that was science. Now let's go back to engineering. How do we put this in the hands of customers? How do we make sure that as many researchers, as many practitioners, and eventually as many people can benefit from those models? I'm going to do a quick check on time because I don't have the... Okay, we're doing good. So yes, industrializing transformers is hard, and I showed you how Tesla, Google, Microsoft, Facebook are able to run billions of predictions of transformers models, large language models, and other models a day. But that requires a lot of very specific skills as you go from deploying the model, which is already challenging, to optimizing the model, and eventually to optimizing the model to the hardware. And rare are the companies that have the in-house skill sets to do all of these things. We try to make that available to companies as a service through our hosted machine learning platform. But for companies that try to do this in-house, it's very challenging. So what I've observed through hundreds of conversations with practitioners and companies is that typically for companies that want to deploy those models in production with good enough latency to have very high throughput or to enable real-time customer interaction, it takes typically 2 months with their best machine learning engineers to be able to achieve that using their infrastructure. So that's why it's important to make those innovations, those techniques, those speed ups available to as many people as possible. And so that's the main theme of our partnership and strategic collaboration with Intel. We're happy to work with them and have their support to make sure that the best hardware-specific optimization and acceleration libraries, tools, and techniques can make their way to transformers users. And so we're working hand in hand with them to make sure that for instance, the AVX 512 instruction set with Intel TensorFlow is available to our users, and it is now available through the Transformers library making sure that the latest tuning, pruning, quantization, and hyperparameter optimization techniques can be available to customers so they can get the most out of their hardware. And part of it is enabling through software, but the other way, I talked to how it is rare at companies to have the skill set to be able to finally configure and tune the model configuration on hardware to get the best speed up. So that's why product education is so important. So in collaboration with Intel, we released an in-depth a view of how you can take advantage of the features and capabilities of the latest generation of CPUs, things like multi-threading, optimizing the core count via scaling, batch size scaling, all in order to enable multiple stream inference, being able to do more on the same hardware. So yeah, same as before. Head to our blog at hf.co/blog if you want to learn more about this. But super pumped to continue working with Intel to make sure that not only we make the latest science accessible to people, but also we make sure that companies can leverage those in the most compute efficient way. And the end result for all this is that we were able, through all the different approaches and optimization techniques and collaborations that I mentioned, we're able to reliably get end-to-end latency inference. I mean end-to-end, including pre-processing, post-processing, and the request to go from request to response from a customer perspective under 10 milliseconds on BERT-like models, which is really, really exciting to me. We all know how transformative the accuracy boost has been with transformers for machine learning. But historically, these models have been slow and expensive to run. So we are excited to be on our way to make those super accurate models much more compute efficient, much faster, so that as many people in the world can reap benefit from them. So I will conclude this talk by going back to my initial guess and my initial guess game. What is the common thread between all this? It's transformers. And what is the goal of what we're doing is that every single person in the world can benefit from the productivity boost that these language models, speech models, vision models, and other modalities provide. So yeah, thank you very much for inviting me, and I'll be happy to take your questions.
Thank you, Jeff. That was very informative. I see we already have a hand up. Kushal.
Thanks, Jeff. That was a very good presentation. I just have, so there's another answer to the question that you asked, right? Wish I had bought the shares in time. Just a couple of things. So when you say end-to-end latency, right, less than 10 milliseconds, is that batch one?
So it's batch one.
Yeah.
And yeah.
And then, so do you know what's the requirement behind this? Is that what kind of use cases is behind this requirement, 10 millisecond?
Yeah, of course. And even before I get to the requirements, like one interesting observation is that Hugging Face being at the center of the ecosystem of the usage of transformer models, we can see sort of the evolution of the adoption curve of these different models, architectures, tasks, and modalities across the industry as they move from the researchers to the data scientists to features that are in customers' hands. And so today, like the models and tasks that have gone through this whole cycle of maturity are definitely the NLP models, and within NLP models, the BERT-like models represent about 3/4 of what end users are using to serve predictions. And so yeah, you were talking about the requirements. So the use cases that are powered by that is either high throughput or real-time use cases. So Gmail autocomplete is a great example of that. You're typing, and as you're typing each keystroke, a new prediction is being made. You want these predictions to be made within single-digit milliseconds, so that when you add the network latency to this, the customer gets a visual feedback within 50 milliseconds. That's typically what consumer-facing experiences will require. Another very wide use case is search. Right, when you're typing search queries, you're expecting not only to get results very quickly, but even to get suggestions as to what your query actually is or should complete very, very fast. And search engines are everywhere. I mean, we all use Google, yes, but every time we go shopping, every time we use a social network, whatever, we all use search. And so being able to have better results through semantic search is something that language models enable by building a vectorized representation of your knowledge base. And so, yes, very fast inference enables that.
Thank you. That's very good to know. And if you we don't have to do it now. You talked about in the next slide. You talked about the optimizations you have done. So I think there are trade-offs that you guys have done with respect to memory utilization and computation. So if you can direct us to any blogs or papers that you have on them, that will be very useful. Thank you.
Of course.
Right. We have a few more minutes as we go into the break. We have a question from Sudeep. Please go ahead.
Yeah, so excellent talk, Jeff. I wanted to know what sort of efficiency metrics do you see in production, inferences per second per watt, types of model sizes, what type of ranges do you see?
Thank you, great question. And while I was listening, I pasted in the chat of the teams the article I mentioned where we talk about all the different knobs and features one can use to optimize inference on a latest gen Intel CPU. And so your question, it kind of depends at which layer of the stack we're talking. If we're talking to the cloud, to the clouds, for instance, throughput is typically throughput is of course a function of latency, but throughput is really the main goal. We're happy to have a great strategic collaboration with AWS to enable people to work with our models from training to inference within SageMaker, their ML environment. And so, yes, discussions usually revolve around how can we increase the throughput by being more efficient so that customers can do more on a given instance or have the choice to use smaller instances to run their models. But then if you go down the stack, when we talk to companies like e-commerce companies or financial service companies, well, less for them because money is less of an issue. But when we talk to companies, typically it's the total cost that is being looked. And so when you looked at the total cost of operation, it's the latency is a huge factor because it linearly influences your cost. But what also influences your cost is the memory requirement. So that's where a method like the block pruning method that I was explaining, which is still at the science stage, can yield great benefits because it means that you can actually run this model on a smaller GPU, or maybe you don't even need a GPU at all. Yeah.
Okay, thanks.
All right. We are almost heading into the break, but we have a question from Shigang. If that's a quick question, Shigang, please go ahead.
Yes, I think it's a quick question. So, hi Jeff, thanks for your great talk. So, mixture of experts is also another method for sparse training. So, what's the connection between MOE and block pruning? And can block pruning works together with MOE to further reduce the compute complexity?
Yes, and say again the MOE?
I mean, can block pruning works together with a mixture of expert to further reduce the compute complexity?
Yes, that's right. So, so distillation has shown amazing results to accelerate models, but traditionally pruning methods have shown great results to reduce the memory requirements, but not to accelerate models, because unstructured sparsity is hard to, at the hardware level, traduce to yield efficiency gain. The computational cost remains similar. That's why using block pruning as the way to do pruning yields much better results, because all the way down to the hardware, it translates these smaller models into faster models. And so it's really combining this block pruning with distillation that has produced the best results for us.
Okay, thanks.
All right. We'll take a short break and come back at 11. Thank you, Jeff, again for the talk. I hope you stick around for a little bit more if you like.
Thank you.